So far we have discussed about the primary edge detection technique. Now we'll talk about the Canny edge detector. Canny edge operator works in the following way. First, filter the image with the derivative of Gaussian. Then find the magnitude and orientation of gradient. Next we do what we call the non-maximum suppression, which is the thinning that we will talk about a minute later. Then there is a linking operation where we're gonna detect we're gonna use two thresholds, low and high, and use the high threshold to start edge curves and the lower threshold to continue them. So to illustrate the Canny edge detector, we start with the Lena image, and if we are to take just the magnitude and gradient, it looks like this. We can see here it's just the magnitude and magnitude of the gradient. It looks close to edges. It's somehow when we see it, it looks like edge, but it's just a gradient image. And next we can threshold that gradient image. Now we can see a bunch of stops going which has gone away, and the gradient which is not high enough is removed. We can see like here the edge looks more clearer than just only the gradient. Here lots of like details have been removed. And then we do operation called thinning. We can see here, which we call non-maximum suppression. And in the thinning we can see like it's the thinnest version of the edge, and basically saying what we have got a bunch of points that exceeds the threshold locally, and we will pull it out that exceeds the most. And what we do is that it's just the thin version of this thin version of this thresholded edge. And the question arises why we need to do this thinning operation. Here let's look at this image, and this is the Lena image and the gradient image of this Lena image. And if we take just a small version, small part of this, small segment of this this image, we can see that there is a kind of thick part that exceeds the threshold. We can see now if we plot this as a 1D function, like it starts with the lower value and goes up, and when we take the first derivative of this profile, intensity profile, what we found is like the first derivative exceeds, like some part of the first derivative exceeds the threshold, and this value that exceeds this threshold gives us the thick edge. So we want to turn it into a thinner edge. So the way of non-maximal suppression, like the thinning is done in Canny operator like this. We'll see here, like in non-maximal suppression we try to find edge points, or like to find the edge points we need to find the local maxima of the gradient magnitude, and broad ridges must be thinned so that only magnitudes at the point of greatest local change remain, and all the values along the direction of gradient that are not peak values of the ridge are suppressed. We can see here is this is the set of intensity value, and we can see here the value we can see here the direction of edge. And what we do is we consider the pixel magnitude on the direction of a gradient, and we compare these values with the edge pixel. And if the magnitude, like let's say that this is represented by pixel magnitude of ij, and if this magnitude ij is less than its nearby magnitude along the direction of gradient, and like there are two magnitudes, one is magnitude I1, magnitude at I1J1, and another one is magnitude at I2J2. If this magnitude at Ij is less than magnitude of I1J1, or magnitude of Ij is less than magnitude of I2J2, then we will make this value to 0, or we will suppress this. Otherwise we will retain its value. So what happens is we get the thinned value. However, with the thinned image also it comes with some problem, like the pixels along the edge didn't survive the thresholding. We can see here that the edge got discontinued in this area, so it may also come with some problem. So what we have to do is we apply high threshold to detect the strong edge pixels and link those edge pixels to form the strong edges, and again we apply low threshold to find the weak edges, weak but plausible edge pixels, and extend the strong edge to follow the weak edge pixels. Let's see in more detail about this. Like this is the hysteresis thresholding or edge linking. As we have said before, that the output of non-maxima suppression still contains the local maxima created by the noise. So can we get rid of them just by using the single threshold? If we set the low threshold, some noisy maxima will be accepted too, and if we set high threshold, true maxima might be missed. The value of true maxima will fluctuate above and below the threshold, and that will result in fragmenting the edge. So a more effective scheme is to use two thresholds, a low threshold TL and a high threshold TH, and it's usually TH is set as a double of TL. So we can see here, we check the maximum value of gradient value is sufficiently large or dropouts, so we use hysteresis, use the high threshold to start edge curves and low threshold to continue them. And here is the example of hysteresis thresholding. We have got the original image, and with high threshold and with low threshold and hysteresis threshold, we can see here in high threshold there are lots of discontinuities of edges, and in low threshold it consists of lots of unnecessary details which may be created by noise or some other source. And with the hysteresis threshold we get just like the required details of the image. We can see like there is no more discontinuity in edges, as well as unnecessary details are not included in this hysteresis thresholded image. Okay, now let's talk about again the edge detection using the second derivative. What we have studied, as like we have discussed earlier about the one-dimensional case of second derivative of Gaussian. So we have here is our original Gaussian. Here is the original Gaussian, and when we applied the second derivative of this Gaussian, will look like this. It is second derivative Gaussian, which is the Mexican hat operator, and which is the it is the inverted Mexican hat operator. And when we applied that to f, this function, it's same thing as taking the second derivative of the smooth version. So we were looking for the zero crossing on the bottom of the graph, and that corresponds to where the edges are. This is the zero crossing, and this will give us about the This will tell us about where the edge is located, and it's in 1D. Now when we talk about this in 2D, we have got the 2D function here, and here g x and y gives x and y direction, and sigma gives the standard deviation, and here we have got the Laplacian operator, which is the second order, like this is the second order differential equation. And if we combine these two, this Gaussian and Laplacian operator, we get this expression, and it results in the, when we plot this, we will get a Mexican hat operator, and it looks like this. This is our Mexican hat operator, and when we apply this in this original image with the Laplacian of Gaussian, we get the standard deviation of 1. With the standard deviation of 1, we'll get this image as a result of applying Laplacian of Gaussian. And well, we will be this I have just here I have just give some just simply the introduction of Laplacian of Gaussian. It's very useful in computer vision, and we will be discussing in more detail about Laplacian of Gaussian in our subsequent classes, because it's frequently used in feature detection and feature extraction and detection, and that will be discussed in our subsequent classes.